Okay, hi everyone. I'm making this screencast in order to explain the inverse function theorem, which is the most important and first local classification result for smooth maps. It says that if we have a map, a smooth map F from M to N, sending the point P to Q, and if this is a smooth map between n-dimensional manifolds, so manifolds of the same dimension, and if we know that the derivative at P is invertible, then there's a local smooth inverse. Okay? So that's a pointwise condition. We just know that the derivative is invertible at the point P, and that tells us that the map is invertible in a neighborhood of P. So more specifically, what we're gonna need to show is that there's an open set of P, an open set of P, an open set of Q, and an inverse that takes V to U, so that we have F going from U to V, G going from V to U, and their inverses, meaning that FG and GF are given by the appropriate identity maps. Okay, so this theorem the proof of this theorem has several parts. Step 0 is going to be just a setup. Step 1 is going to be a construction of the map G. So we need to actually come up with a way of producing the inverse. And the main tool for producing that inverse is the Banach fixed point theorem. So I'm just going to cover that briefly first. Once we have constructed this inverse map, then in step 2, we need to show that it's continuous. In step 3, we're going to use that continuous inverse and show that the map F is a local homeomorphism. Okay. Once we know that it's a local homeomorphism, the only remaining part is to show that it's actually smooth. And so in step 4, we show that it's differentiable at every point. And in step 5, we show that it's actually infinitely differentiable. So our arbitrary number of derivatives. And I'll put these notes up on the web page. Okay, so the main tool that we're going to use to construct the inverse is called the Banach fixed point theorem. And it's a theorem about fixed points of maps from a certain metric space X to itself. So if we have a self map, a map from X to X, which decreases distances in this way, so that when we apply H, the distance between the resulting points is less than or equal to half of the original distance. Okay, so if that holds, we call H a contraction mapping. And if we have a contraction mapping on a metric space which is complete, which means that Cauchy sequences converge, then there is a fixed point of this map, and that fixed point is unique. Okay, so here we see this is just a typical diagram for explaining the Banach fixed point theorem. We have a domain and a codomain. The domain is the interval 0, 1, and the codomain is this is a map from 0, 1 to itself, but I'm just drawing the graph of this map is drawn in blue here. So the typical thing that you often see is that you start with a certain right. So what I want to just mention is that in the proof of the Banach fixed point theorem, the existence of this unique fixed point, it's not just an existence result in a sense. There's a specific way of obtaining that fixed point, which is just iterate the map. So you just choose an arbitrary initial point, which I'm denoting as the first point here. You apply the map. So that means that you just look at what the value of this map is. Now this new point is a point in the interval again, and typically the way graphically you find it is that you just follow a horizontal line until you get to the diagonal, and then that is your second point. Okay, so 1 is sent to this point, which is really the same as this point. So 1 is sent to 2. That's the first application of the map. Then we apply the map to 2, and we kind of follow that up here and get our third point. And to see where that is in the original domain, we just follow a horizontal line to the to the diagonal, and that is our third point, 3. Okay, and we just keep doing that, and you know, this will basically be this kind of rectangular path that spirals in and hits eventually in a limit the fixed point, which is somewhere around here. That's what I've denoted here, the fixed point. Fixed point is exactly where the graph of this function agrees with the diagonal. So it's that intersection point right there. Okay, so all right, so we're going to come up with a way of finding the inverse using this fixed point theorem. But before we do that, we just want to simplify the setup of the problem. So the theorem is phrased in terms of manifolds M and N, but we know that this is a local result, so we can choose charts around P and a chart around Q, so that P and Q are the origin in the chart. So that means that I'm going to take M to be just an open in Rn, an open neighborhood of the origin in Rn, and N is just, again, Rn. And we can take P and Q to be the origin. And the statement of the theorem is that the derivative is invertible. But if I just replace this map by f composed with this linear map, which is this invertible derivative, then this new smooth map is going to have derivative just equal to the identity matrix. So in other words, what this means is that by doing a linear change of coordinates, you can arrange that you basically have a map f from Rn to Rn, sending the origin to the origin, and such that the derivative is taking the tangent space to the tangent space by the identity map. Okay, and this is the setup that we're going to work with. We're going to locally invert this function, this map. Okay, so the first step is to actually define the inverse map, which we're going to call G. So the idea is that you know, if I have a point in the codomain y, okay, I would like to produce the inverse applied to y. So the question is, I need to find the point x in the domain, so that if I apply f to it, I get y. And the idea is that for a fixed y, in order to find this point x, I'm going to express it as the fixed point of a contraction mapping. So that contraction mapping is going to depend on the point y that I am trying to invert. Okay. So this, I've written it here, that for each y sufficiently small, since this is a local inversion, we are trying to find this x such that f of x equals y, and what we're going to do is arrange that it be the fixed point of a contraction map. So in this sense, it is the Banach fixed point theorem which will literally invert the map f. Okay, so in order to do that, the first task is simply to express x in terms of some map, so that x is a fixed point of some map. So the convenient way of doing that is the following. So we take this this map f, and we break it up into its linear part, which is just the identity map, and its nonlinear part, which is just whatever else is remaining. So we have k of x is the nonlinear part of x. And if if f of x is equal to y, we get this equation. And so as a result, we can kind of solve for x in a sense, but we're not really solving for x because x still occurs in the left-hand side. But basically, we now have this map. So if we think of the left-hand side as a map which takes x to y minus k of x, then indeed, if we have a fixed point of this map, that means that this would equal x, and therefore that would mean that y is equal to f of x. So it's exactly this which is defining us our mapping, for which the fixed points are the inverses of the required inverse. Okay, so here this is the important definition. We have we have a map. Okay, and this is a map from the x space to itself. Okay. It takes a point x and sends it to this constant vector y minus this nonlinear part of the function f. And a fixed point of hy is exactly going to be a point which is sent to y by f. Okay, so all we need to do now is check that, first of all, this hy is a contraction map. And we also need to check that there is a subdomain inside Rn where it is that it's acting upon, and we want that subdomain to be compact so that as a metric space it's complete. Okay, so if we could prove, so in other words, if hy is a map from Rn to Rn, and if it's a contraction map, that's not enough because Rn is not complete. So we need to kind of show that there's some closed ball or a compact ball in Rn such that h of y sends it to itself, and then we will be able to get a unique fixed point. So okay, the first question is, why is it actually a contraction map? So okay, sorry, let's take a look at this again. So if h of y is given by a constant vector minus k of x, then the derivative of h of y doesn't see y, so y, the derivative of this term is 0, and we get the derivative of this nonlinear term. But the derivative of hy at the origin is 0. And so that means that in some small ball around the origin, the derivative is guaranteed to be smaller than a half. And that means that if we choose any 2 points in that ball, okay, then their distance will be decreased when you apply h of y, because the derivative of h of y is small. So the mean value theorem tells us that the distance between the resulting 2 points is less than or equal to 1/2 times the original distance. And so that is showing us that it is in fact a contraction map. Okay. Now we need to be careful because it could be that I have my 2 points x and x prime, and maybe they're mapped out here somewhere, and the distance between them is decreased, but the actual position is that they're being moved quite far out. So instead, what we need to check is that actually hy can restrict to a closed ball. Okay, so in order to see that, we need to somehow measure the absolute size of the result of hyx. So the actual norm of hyx, acting on a single point x, if I just write this expression and use the triangle inequality, what I get is that the size of hyx is less than or equal to this size, which, because it's a contraction map, is bounded by a half of the norm of x, and this size, which, if you just look at where the origin is sent to y, and so that has the norm of y. So that means that actually such points x or x prime, they could actually be moved quite far away if y is large. So what we're going to do is make sure that the y that we're choosing, that this is the fixed vector y that we're trying to invert, we have to make sure that this thing is chosen to be very small, so in a small ball of radius r/2. And if this is of size r/2 and if this is of size r, then this thing is of size r. So what this shows is that as long as the point y that we're interested in inverting is chosen small enough, then hy is a map from the closed ball to the closed ball of radius r. And therefore, it is a contraction mapping on a complete metric space, and the Banach fixed point theorem allows us to conclude that there's a unique fixed point in this closed ball. Okay, so that's it. So that allows us to define our inverse map. The inverse map is defined in the following way. For y inside the ball of radius r/2, we send it to whatever is the unique fixed point guaranteed by the Banach fixed point theorem, the fixed point of this map h sub y. So for each y, we're applying the Banach fixed point theorem to a different contraction mapping. So we have a huge number of contraction mappings, one for every point in the codomain, and that means that we get all of our parametrized inverses parametrized by y. Okay, so at this point, just need to be a little careful to check that the thing that we have actually built, this bizarre map G, is actually an inverse, at least set theoretically. It's a set theoretic inverse. So why is that? Well, if we apply f composed G, okay, that means that for a point y inside the ball of radius r/2, we apply G, that produces our fixed point, then we apply F, and because G is a fixed point, that guarantees that, that this is sent to the original point y. So, in other words, this composition is the identity because of the fact that, that y is sent by G to a fixed point of this hy map. What about the other direction? So if you apply F first and then G, that gives an identity. So in order for this to be defined, we need to make sure that we're applying it to a point which is in the closed ball of radius r, intersect the pre-image by F of this smaller ball. So that this is the subset where this composition is actually defined. And the reason why this is true is because of the uniqueness of the fixed point, right? So you could think about that one direction of the composition being the identity is given by the fixed point property, and the other direction is given by the uniqueness of the fixed point. Okay, but the problem is that what we wanted to prove for the original theorem is that we need to show that there are open subsets surrounding P and Q, so that F has an inverse on these, on these open subsets. But the problem is that we're dealing with this closed ball, and so we are not guaranteed that this subset where we have this inverse relationship, this subset, although it is open in this closed ball, it may not be open in the original manifold. So the idea is that we want to, so just to draw a picture, it could be that what we're looking at is something that, we have this closed ball, and we have this smaller open ball. So this is our, oops, sorry. So this is, let's say, radius r, and this is r/2. Okay, so this is an open set, and the pre-image of that could be something like, something like this. A priori, it could be something like this, and that is an open subset of this closed ball, but it's not an open subset of the ambient space. So the task is really that what we're going to need to do is to kind of shrink this open ball to a smaller one, right? And look at that preimage and hope that that is giving us a small open subset in the domain, and that's what we're going to take as U, and this is what we'll take as V. Okay. So let's see how that works. But before arranging that or fixing this small issue, we're going to need to show that G is actually a continuous map. So because of the funny way that we defined it as a collection of fixed points for various different maps. It's totally, it's not completely obvious that G is continuous. So to show that it's continuous, we do the standard proof. We look at the size of G of y minus G of y prime, try to bound it by the size of y minus y prime. So we use the fact that these are fixed points, so G of y is h applied to G of y, and G of y prime is h of y prime applied to G of y prime. So notice that these are different y's, different points in the codomain. And so we know how to bound this if this was the same y. So what we do is just use the expression for h of y. There's a constant term which comes out, and then there's this nonlinear term. And right, and so this difference now, you could think of it as, let me write this. So this difference here, that's really the same thing as h y of G of y minus h y of G of y prime, right? With the same y, just because the constant terms would cancel out and we would only get the nonlinear terms. And we know that this thing is a contraction map, so that's 1/2 of G of y minus G of y prime. Okay, and so that's how we get this. And so then we can just take this and bring it over to the left-hand side, and we see that indeed we managed to bound the difference between the results by a constant times the difference between the inputs, and so G is continuous. Okay, now that G is continuous, we could actually use it in order to produce, so we have this map G which is going from here to there, right? And so what we could do is take a small open set inside this closed ball, and then take the preimage under G to define V. That would be a way of ensuring that we have an open set which is being mapped to an open set. So we use the continuity of G. Oh, and the fact that that G actually takes 0 to 0, because if we go back to the map HY, if y is actually equal to 0, then the map is x goes to k of x, or minus k of x, right? So if y is equal to 0, then h of x is k of x, and the fixed point is what? Well, the fixed point is x equals 0. So this means that y equals 0 is sent to x equals 0. So this means that our inverse does indeed do what is required, in the sense that it does send 0 to 0. It's continuous. So this is what we do. We define U to be some neighborhood of the origin inside the open ball, so that it doesn't touch the boundary of this ball. And then V is defined to be G inverse of U. So now we have two open sets. G sends V to U, and F sends U to V. And now we can check the same properties, that they are indeed inverse. F composed with G is the identity on V because of the fixed point property, and G composed with F is the identity on U because of uniqueness. uniqueness of fixed point is guaranteed in this closed ball. So that's how we obtain the fact that F is a local homeomorphism. We just needed to be a bit careful how to define this open set and this open set of the domain and codomain. Okay, so now we need to check that this inverse, so far what do we have? We have a completely smooth map F from U to V, and we have a continuous inverse G, which shows that F is at least a homeomorphism. So it's a local isomorphism for topological manifolds. But in order to be a smooth isomorphism, we need to check that G is differentiable and that all its derivatives exist. So first we check that, let's see, so step 4 is to check that G is differentiable at any point in V. Okay, so the as it usually is the case when we're trying to prove that a function has a derivative, it's often useful to kind of guess what the derivative is and then prove that it satisfies the defining property of the derivative. And because G is an inverse to F, we know that if G were smooth, then the derivative of F and the derivative of G would be inverse to each other by the chain rule. And so that means that we know what the derivative of G is supposed to be. It's supposed to be the inverse of the derivative of F. So this derivative, which we're looking for, it must be given by the inverse of the derivative of F. We just need to check that this inverse, which is well defined, actually is the derivative of this map G. Okay, now we do need to be a tiny bit careful here because the assumption of the theorem tells us that the derivative of F is invertible at 0. Okay, but as I discussed in class, the fact that a matrix is invertible, that's an open condition. If you deform the matrix a little bit, because the determinant function is continuous, a small perturbation of an invertible matrix is still invertible. So, but it could be that we didn't choose our original radius r small enough so that F would be invertible on the entire ball. So the point is that what we could do is just go back and choose r sufficiently small so that F is invertible everywhere in this ball. And so this derivative of F, which is, you should think of it as a matrix which depends on the point in the ball, I just want to make sure that the original ball was chosen small enough so that derivative is always invertible. Okay, and that guarantees that at least we have now a well-defined guess for the derivative of G everywhere on V. So now we need to prove that this inverse operator is actually a derivative of G. So we do the standard thing. We take what happened? Yeah, so the definition of this derivative operator is exactly shown here. So let's say take a look at this left-hand side. Okay, so we see G, and if this inverse operator is the derivative of G, then as by definition, as y prime approaches y, then the limit of this expression should be 0, right? And that's basically the definition of this operator as being the derivative of G, the map G. Okay, so in order to bound this thing, we just apply the following kind of argument. So we're assuming that that g of y and g of y prime are given by these 2 points, x and x prime, which are in U. So this is the numerator of the expression that we're interested in, and this thing is equal to, by definition, x minus x prime minus the derivative applied to the derivative computed at the point x inverse applied to f of x minus f of x prime. So in other words, we're using the fact that g is an inverse of f to write this expression, and then we can take out this operator, and when we take that out, we're going to get dfx applied to this, right, and then this is just how we are going to massage the numerator, divide by y minus y prime, and we get that this whole thing is bounded by this operator dfx, and then this expression. But the point is that because we've taken out this inverse factor, the right-hand side is just the expression for the derivative of the function f. And so as we let y prime approach y, right, as y prime approaches y, then because of the continuity of g, x prime will approach x. If x prime approaches x, then by definition of the derivative of f, this right-hand side goes to 0, and this is just some bounded expression in that open set, and so that means that the whole right-hand side goes to 0. And because of the fact that it bounds the left-hand side goes to 0, and that tells us that g is differentiable at y. Okay, and then there's a kind of slightly tricky observation, which is that now that we have proven that it is differentiable, it's actually C infinity. Why is that? Well, we have an actual expression for the derivative of g at every point y, and that derivative matrix is given by the inverse of the derivative matrix of f. Now, the point is that if you have a matrix and invert it, we can express the inverse, okay, in terms of the original matrix by this kind of polynomial expression. It's like 1 over the determinant multiplied by the adjugate matrix, right? So when you compute when you take a matrix Aij, right, and you compute its inverse, you're going to get 1 over the determinant, okay, times the determinant and times the adjugate matrix. This adjugate matrix is made up out of the minors of A, and so this thing here is a polynomial in the entries of the original matrix. And this 1 over determinant, that's 1 over a polynomial, and we're assuming that determinant is non-zero in this region. So that means that we have a polynomial, this matrix here is a bunch of polynomials divided by an overall non-vanishing polynomial. And so that means that if the entries of the matrix are smooth functions, which they are because f is C infinity, then when we take the inverse of the matrix, the entries will be polynomial expressions in those smooth functions. And so this thing is guaranteed to be C infinity. So that's how I've written it here. Because of the fact that inversion itself as a map is C infinity, that means that this derivative is just a composite of a smooth operator composed with the inversion, which is also smooth. And so that means that g is as differentiable as f is. Okay, and so that completes the proof, showing that this inverse that we've constructed is infinitely differentiable.